Hello, my name is Kelly Caldwell and I'm the lead instructor at Stanley Community College's Instructor Training Center. This is going to be a lecture on one of the many modules in the different courses inside of Cisco Networking Academy. I'm going to cover many different items in these particular lectures, starting with CCNA, going possibly all the way through DevNet. But to begin with, one of the things I want you to know is I go with a good enough philosophy, and that is no lecture is perfect. So in other words, if you're in the classroom with me, we could be interrupted by a person knocking on the door, my phone could ding, your phone could ding. I'm not going to have perfect lectures, and therefore my recorded lectures will not be perfect. You may hear my phone ding, you may hear a phone call start during one of the lectures, and I'll pause the lecture and then start back over. I'm trying to give you a good enough lecture to help you learn the materials. I also want you to know if you are not taking classes at a Cisco Academy, in other words, you're watching these videos on my YouTube channel and you're not trying to participate in an actual Cisco Academy, I strongly recommend that you go to www.netacad.com, scroll all the way to the bottom to where it says Find an Academy. I'm going to put in here the state, city that we are in. So in case I am in Albemarle, NC, North Carolina, as you can probably tell by my accent. But you'll see here Stanley Community College, and if you click here, you would get the information on what courses we offer and how to get in contact with us and how to actually see our offerings. So if you are in an area and you would like to find your local school or Cisco Networking Academy, then go to netacad.com, scroll to the bottom, and do Find an Academy. I strongly recommend that you get involved in the Cisco Networking Academy because it is a wonderful, wonderful program. Last but not least, enjoy, learn, and grow. So enjoy these lectures, learn from them, grow. If you want to grow in the IT field, that's excellent. Or if you just want to learn new things, that's even better too. We hope these lectures will be useful for you and that you will be able to use them to increase your knowledge in the IT field. Hello and welcome to a Module 5 lecture for Introduction to Networks, version 7.02. This particular module is going to look at number systems and also how to calculate between different numbering systems. We're going to start out talking about what our number system is. Now, binary and IPv4 addresses. IPv4 addresses we've talked just a little bit about, but not much. We talked about the fact that binary is a base 2 numbering system, and that IPv4 addresses or IP addresses are addresses kind of like a phone number. Those addresses typically consist of a number. So let's say it may be 192.168. And I apologize for my handwriting, folks, but I have been two things. One, I'm left-handed. Two, I was hit by a truck several years ago and paralyzed from the neck down. So it's a miracle I can write it all. But this is an IP address, 192.168.12.0, and it is in dotted decimal format. However, the computer doesn't see dotted decimal. The computer itself sees binary. So everything the computer does is in binary. So we're going to learn how to do a conversion from binary to decimal and decimal to binary. That's part of this entire module. Here's the dotted decimal format. So this 192.168.10.10 is this binary number right here. And we'll show you how to convert these 32 bits from decimal to binary and binary to decimal here shortly. There's a good video here, but really one of the things I want you to be made aware of is that we are most familiar with a base 10 numbering system. So if we get out here and we look, we think about a base, oops, hit the wrong button there. Hold on one second. If we look at a base 10 numbering system, so we're looking at base 10. All right. If we go out here and I say you have $101, what you really have is looking at, we have 10 to the zeros position, the ones position. We have 10 to the ones position, or the tens, and 10 to the two positions, which is the 100. So you actually have 1 1, 0 tens, and 1 100. That's 101 in a base 10 numbering system. Likewise, if you had 53, all right, you would have 3 ones and 5 tens. Now, we're accustomed to this, and really, you think about, why do we use a primary base 10 numbering system? Well, just look down at your hands, folks. We have 5 fingers on each hand, so we have a base 10 numbering system. However, this numbering system is not the best system to use for computers. Computers use a base 2 numbering system or a binary system. In that binary system, I do want to go back 1 second and kind of make you aware of something we don't even think about, and that is this. Inside of our base 10 numbering systems, okay, we don't even think about the fact that we use the digits 0, keep hitting the wrong button there. We use the digits 0 and through 9, 0 through 9. So in all of our positions. So if you think about it down here, when we're looking at these positions, we are using inside each one of these particular positions, we can go from 0 to 9. Can't go any further than that because we don't have the ability to do that. In a base 2 numbering system, it's going to be completely different. What we're going to do is we're going to use, in a base 2 numbering system, we're only going to have 2 values we can use, and that is a 0 and a 1. So we have 2 positions, and that's it. We also will find out that we've got 2 to the 0, okay, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, 2 to the 6th, and 2 to the 7th. And you'll learn that each one of these positions has a value of 1, 2, 4, 8, 16, 32, 64, and then way out here it's 128. So you're going to learn that if we do a binary number that is 1, 0, 0, 0, 0, 0, 0, 0. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Yep, you got 8 numbers here. And if you add that all together, so you've got 0 1s, 0 2s, 0 4s, 0 8s, 0 16s, 0 32s, and 0 64s. So the decimal value here is 128. Okay, because that's the only bit position turned on. All right. So a base 2 numbering system has 2 positions possible, or 2 different notations that we values. We're going to have a 0 or 1, on or off. And then we use 2 as our positional notation. So 2 to the 0, and you can go past 2 to the 7th. You can go 2 to the 8th, which is 256, 2 to the 9th, which is 512, and so on and so forth. But since we're dealing with typically just 32-bit addresses, and each one of them are 4 octets, so 4 8-bit positions, 2 to the 0, 2 to the 7th handles most of our needs. So we can see here again, this is binary notation for a typical base 10 numbering system, so 10 to the 0. So if we had 3,210, we would have, actually, sorry, they're showing you the bit positions here. 10 to the 0, which is 1, 10 to the 1 is 10, 10 to the 2 is 2, and 10 to the 3 is 1,000. So if we had a value of 1,005, we would have 1 in the 10 to the 3rd position, 0 in the 100 position, 0 in the 10 position, and 5 in the 1s position. That would give you 1,005. So very similar to what we have here. You see they got 1,234, gives you 1 in the thousands, 2 in the hundreds, 3 in the tens, and 4 in the ones. Well, in our base 2 numbering system, it's exactly what I showed you here, 2 to the 0 through 2 to the 7th. And each one of those positions has a value between 1 and 128. Then when we go to calculate a particular value, we do it by adding, when we want to convert from binary to decimal, we use the additive or addition method. So we'll go in here and say, okay, the 128 is turned on. Okay, so 128 plus, in this case, 64 is turned on. So we'll add 64 to it. And then nothing else is turned on. So those are all zeros. So our value of 11000000 would be 192. So let's look real quick. Let's look at converting binary to decimal. Let's go over here. Go back to our notepad. So we're converting binary to decimal. We use, when we do this, we're going to use the addition method. Okay. addition method to convert from binary to decimal. So again, if you had the value 1100000001, what you would do is you would take and say, okay, 128, because this turned on, plus, all right, what else turned on? 64 is turned on, plus 1, and you're going to learn that is 193. The other thing I can teach you, and I will teach you in a minute, is where these positions break down and make it a little bit easier on you. So that is 193, so we added those values together. By the way, if the one value is turned on, it will always be an odd number. If the one value is turned off, it will always be an even number. So that's one thing you can kind of check yourself. So if I did 111000010, and then thought I come up with an odd number, I know that's incorrect, because with that turned off, it must be an even number. This, by the way, is 224 plus 2. So it's actually 128 plus 64 plus 32 plus 2. So it'd be 8, 9, 10, 16. Okay, came a 1, and ends up being 226. Okay. And the reason I know that is because I know that if the first 3 bits are turned on, it's 224, and then add 2 to it, it gives me 226. So anytime we're converting from binary to decimal, we use the addition method for that particular function, or to do that. So again, are all types of examples. They've got, in fact, this is one of the neatest things in here. They give you a number and say, what is the decimal value? In this case, I know it's 128 because it's the first value on and nothing else. Check. Correct. New number. And it will just keep feeding me numbers. So 36 is 48 plus 1 is 49. Again, I would know this has to be an odd number because the one value is turned on. Check it. Correct. New number. So you can practice as much as you want binary to decimal conversion. Just remember, it's the addition method to do binary to decimal. Now, if we're going to do decimal to binary, so we're going to do decimal to binary, we do the subtraction method. So again, apologize for my handwriting, folks. Again, the fact I'm left-handed and can barely use my hands and have been hit by a truck are all pretty amazing that I can do anything at all. So let's imagine 192, and I want to convert that to binary. The first thing I'm going to do is I would write out, honestly, 2 to the 7, 2 to the 6, 2 to the 5, 2 to the 4, 2 to the 3, 2 to the 2, 2 to the 1, 2 to the 0, and put those values here. So 1, 2, 4, 8. That's an 8. 16, 32, 64, and then 128. So what we'll do is we'll say, can I subtract 128 from 192? The answer is yes. And then I get the value there, and it'd be 64 left over. All right. So I put a 1 there. Can I subtract 64 from 64? The answer is yes. So I subtract 64, put a 1 there. Since there's nothing left, we've got 0, and everything else is zeros. So 192 becomes 11000000. A very simple system to do this, folks. So when I go back over and look in the curriculum and you look at the decimal to binary conversion, it is simply the subtraction method. Can you subtract it? If the answer is yes, you put a 1 there, subtract it, and then look for the next slot. Can you subtract it from there? If the answer is yes, put a 1 there. If not, put a 0 and move on until you get all the way down to the conversion is over. So again, 192, that's our example we used. Very simple, but this is right here. 192 is the example for this. So step 1, step 2, and then step 3 would be all zeros. Now for the 168, you subtract, put 1 there. So yes, you can subtract 128 from 168 with a remainder of 40. But then you go, okay, next item would be, can I subtract 64 from 40? The answer is no, I cannot. So you put a 0 there and go to the next position. Can I subtract 32 from 40? Yes, I can. put a 1 in there, subtract it. I've got 8 left over. Now I know it's going to be 0, 1, 0, 0, 0 because I can't subtract 16 from 8. However, I can subtract 8 from 8. And then everything else, since there's a remainder now of 0, all these others will be 0. So 168 is 1, 0, 1, 0, 1, 0, 0, 0. Very simple. The beauty here, folks, is again, we've got an activity for you to do. Very simple. You go in here and say, can I subtract 128 from 50? No. Can I subtract 64? No. Can I subtract 32? Yes, I can. All right. What's left over? Should be 18, right? So let's see here. Next thing, can I subtract 16? Yes. That leaves me with 2. I can't subtract 8 from 2. I can't subtract 4 from 2. But I can subtract 2 from 2 with a remainder of 0. And that is correct. So the number 50 in binary is 0, 0, 1, 1, 0, 0, 1, 0. And if you see this on a calculator, they'll probably drop the leading zeros and just give you 1, 1, 0, 0, 1, 0. But when we're working in IPv4 addresses, we need all 8-bit positions in the octet to be shown. So we'd have to do 0, 0, 1, 1, 0, 0, 1, 0. So a very simple conversion, easy to do. Remember, if you're going from decimal to binary, it's the subtraction method. If it's binary to decimal, it's the addition method. And then here's our IPv4 addresses. See them in dotted decimal, the top form here. The bottom form shows it in binary, the way the computer actually deals with it. And the reason they call it 32-bit addresses is because once you convert the dotted decimal to binary, you'll notice there are 32-bit positions. That's why IPv4 is a 32-bit addressing scheme, because there are 32 bits. The other numbering system that we will be using in this course, especially when we get into IPv6 addresses, is hexadecimal. Hexadecimal is a base 16 numbering system. So it's a little bit different because it uses the values 0 through 9. And then we need a way, because it's a base 16 system, we've got to have a way to represent 11 through 15. Well, we can't do that with numbers because we've already used 0 through 9. So A through F represent 11 through 15. Binary, you can see this is, by the way, what a IPv6 address looks like. And inside of each one of these, their unofficial name is called a hextet. But inside of each of these hextet, there are 4 hexadecimal digits, which each 16 binary digits. So there's 4, 8, 12, 16 binary digits in this hextet. Converting from decimal to hexadecimal, you really have to convert to get to hexadecimal. You convert the decimal to binary and then the binary to hexadecimal. So with this, if I wanted to convert 168 to hex, I have to first convert it to binary and then break the binary into 2 groups, which are each 4 bits, and then take that and convert it to hex. So 1000 is 8 and 1010 is A. So 168 in hexadecimal is A8. So if you want to convert hexadecimal to decimal, you have to convert it to 4-bit binary strings, then convert those binary strings into hexadecimal. So this is hexadecimal to binary. So you take D2, convert it into 4-bit strings, put those together, and then that is your binary equivalent. And then you figure the decimal equivalent using the additive method. So it'll be 128 plus 64 plus 32 plus 2, which would be 210. So you'll notice getting from decimal to hexadecimal and hexadecimal to decimal takes a lot more work. Luckily, we rarely convert from decimal to hexadecimal, hexadecimal to decimal. We're normally converting from hex to binary, and that's it. So as we move forward, there's one thing I want to show you that's very useful for you to learn in this process, and that is the following. In a 32-bit setup, if you've got all zeros, so 0, 0, 0, 0, 0, 0, 0, 0, so 1, 2, 3, 4, 5, 6, 7, 8, that value is obviously 0. If it's 1, 0, 0, 0, 0, 0, 0, 0, the value is 128. If it's 1, 1, 0, 0, 0, 0, 0, 0. By the way, I wish I had a dollar for every one or zero I've ever placed on a screen or a board. 192. 1, 1, 1, 0, 0, 0, 0, 0 equals 224. 1, 1, 1, 1, 0, 0, 0, 0 equals 240. 1, 2, 3, 4, 5, 6, 7, 8 equals 248. 1, 2, 3, 4, 5, 6, 7, 8 equals 252. 1, 2, 3, 4, 5, 6, 7, 8 equals 254. And then 1, 2, 3, 4, 5, 6, 7, 8 equals 255. Now, why is it good to learn this? Well, let's imagine I say, okay, convert this to decimal. Well, you can look at this and say, okay, this is 242. And I know that because 111111 is 240. Add 2 to it, this equals 242. If it's 1, 2, 3, 4, 5, 6, 7, 8, then you automatically know that's 254. But also, if you do this, then you can subtract 3 from that and know the value. So it's extremely easy to be able to convert once you know these breakdowns. So I hope this has been a helpful lecture for you. I look forward to seeing you at our next lecture.